You're moving on in your algebra life. You've become an expert at linear functions, and you know that you could graph that. And now we're moving to exponential functions, where the variable is now in the exponent, or the power. And once you get good at these, you're going to be able to graph those, and you're going to realize that exponential functions are very curvy. They don't always curve like that. Sometimes they could curve like this, or even other ways. But we know they're not going to be linear like the functions we've been working with in y equals mx plus b form. So for this intro, we're going to be using the top part of page 1 of the sheet that's going to end up being your homework. And if you have access to the lesson plans, then you have access to this paper with its worked out solutions. If you don't, that's okay. You're still going to be able to get the learning done. Okay, as I mentioned at the beginning, this right here is a review linear function, and if I were to go ahead and complete a t-table and complete a graph like that, it would look like this. So there's really nothing new to see here. You didn't really have to fill out the table to get this done, because you could have known that this was actually a plus 0, meaning my y-intercept was 0, and that the slope was 2, which you could view as 2 over 1 or negative 2 over negative 1, and you could start counting your slope and you'd have your graph. But there's no rule against taking a bunch of x values that were suggested to you, plugging them into the equation, getting out y values, and treating each one of these, say, as a point, 2, 4, plotting that point, and eventually connecting the dots. But all that is review just to remind you of the fundamentals that you will use when you do an exponential function. So now we move over here to the exponential function, and you don't necessarily know something like y equals mx plus b that would allow you to graph that right away. So you would end up filling out a table. And as you notice, they've suggested that we use -3 through 3 for your input or your domain. So I'm going to remind you of how you can get those values on the calculator, but after you get those values on the calculator, you should be able to get your y values, which makes any one of these an ordered pair. For example, -1, 0.5, or 3, 8. And then you could just graph those and you could get this curvy exponential function. So let me remind you of how you would get those on a basic calculator. If I wanted to plug a 3 into here, I would go 3 and then the caret sign raised to, let me redo that. If I'm plugging a 3 in, the 3 is the exponent. So it's 2 raised to the power of 3. So that would be a 2. Then the little caret right there is the exponent, or the power, 2 raised to the 3rd power, and that's how I got the 8. So plugging in the 3, I got out an 8, plugging in the 3 for x. So you can do that, for example, if I plug in a -3, 2 raised to the -3 power, and I get the 0.125. So that's how I get all of these values. I go ahead and turn each one of these into an ordered pair, and now I have my curvy function. It is an exponential function. If you want a little bit of review from the past, my y-intercept, domain, which is all the x values that could exist in this situation, and my x values go forever to the left, and my graph continues to go forever to the right, so my y values span from -infinity to infinity. For my range, or my y values, my graph goes forever upwards, so the largest y value would be infinity, if there can be such a thing, but my graph never gets below this level, which is a y value of 0. So my y values are always bigger than 0, but less than infinity. So before we finish up, I just wanted to show you a couple of things on the calculator that may not be so obvious to you. So here, this looks pretty blurry, but this is a y equals 1/2 to the x. And this is the same problems that are on your homework for tonight. So I have to start plugging an x exponent raised to the base of 1/2. So if I have to do that on the calculator, for example, let's plug in a -2. If I had to plug in the -2, I would start with some parentheses. You could do that, but I'm going to go parentheses 1 fraction 2. So now I have the 1/2, and I'm going to raise that to the -2 power. I use the negative sign down there. So this is calculator speak for 1/2 raised to the -2 power, and I get out a 4, which might be surprising to you. Remember that you might not be using a calculator like this, so you might be using a Desmos calculator online or others, but the bottom line is the caret in almost all situations is going to be the exponent. If the base is a little bit unruly, you're probably better off using some parentheses on there. Let me show you one more. If I go over here to g of x, and now let's plug in, say, a 3. If I plugged in a 3, I would end up having 50 times 0.7 to the 3rd power. At this stage, we would have to honor the wishes of beautiful Princess PEMDAS, and she says, please do any parentheses and exponents before any multiplying. So I can't do the 50 times the 0.7, the multiplying, until I've taken care of the exponents. So here I'll go the 0.7 raised to the 3rd power. So I get a 0.343. So the very next step I would put in my paper is 50 times 0.343 by the orders of beautiful Princess PEMDAS. Now I can multiply by the 50, and I get 17.15. By the way, that means if I were going to graph this, I would have the ordered pair 3, 17.15. Which brings us to the last and final point. When you're graphing these, very frequently you're going to have an adjusted scale. This basic grid works for a lot of our basic y equals mx plus b, but since these functions generally like to do some massive curviness, very frequently your y-axis might have to be larger, or you might go by 10, 20, 30, 40, 50, 60, 70, 80, 90, things like that. So you'll see as we go along. Enjoy your exponential functions.